Welcome to this short introduction video about floating crane stability. In this video we want to learn you a quick scan technique in order to determine the stability of a crane on a barge using a classical principle, the pendulum. We all experienced this pendulum during our physics lessons during our secondary school period, and now we're going to use it. Let's give it a go. Determining the stability of a crane on a barge or a vessel or a pontoon or anything that floats is all about determining the elasticity or the stiffness of the complete system. And now is the recognition of this stiffness is the major point. How do you see this stiffness and how can you calculate this stiffness? In this short introduction video, we want to show you the use of the pendulum principle in order to have a better understanding about what happens and a better and more clear idea about how you can quick scan this stability with a very short calculation. At the right picture you see a floating crane in which two pendulums are drawn. The left one is the pendulum of the load itself hanging on top of the crane, and that's a quite simple one. At the right one you see the famous GM value. We are not going to introduce this GM value in this short video. We think this is common information which most people of you know. We have other videos in which we explain more about this GM value. This GM value is a kind of virtual pendulum. The G value stands for the CUG position, and the M position stands for the rotational point of the crane barge combination as a kind of pivot. So now you have two pendulums which are determining the complete stiffness of the complete situation. At the left picture you see the load. At the middle picture you see the barge represented as a pendulum, which also can be seen at the right picture in green and blue. When you look at the left picture, the load, at the bottom side of it you see the expression which represents the stiffness, the rotational stiffness of a pendulum. It is the mass at the end of the pendulum multiplied by gravitation and the length of the pendulum. For the GM pendulum, it's not any different. It's also the complete mass, so the complete water displacement of the vessel crane combination, multiplied by gravitation and multiplied by the length of the complete pendulum, the GM value. This GM value represents the length of the CUG to the metacentric when the load is interpreted as being acting at the top of the crane. That's very, very important to know, to understand, to recognize. When the load is standing on the deck, it's a complete different situation when the load is getting airborne. So visual, only a centimeter of difference. In real life, it's a big difference concerning stability. This is about these pendulums. In the latest sheet we have seen two pendulums. One of them was the pendulum, the GM value. The length of this pendulum is the GM value. And this GM value is being determined, as we can see in the formula at the left top, by three variables: the width of the barge, the draft of the barge, and the CUG of the barge. This formula we will explain in another short movie. However, for this short introduction movie, we keep it as such, just to give you an indication, nothing more, nothing less. However, just to give you an interpretation of what the width of the barge and the center of gravity does with the stability, a short video. As you can see here, center of gravity is high, the pontoon is small, and when we change these variables by lowering the center of gravity and widening the barge width, the stability increases a lot. Going back with a high center of gravity and a small barge, we'll see ending up with a more fragile system. And that about the GM value. More about GM value in other short introduction videos. Using this test setup explained in the sheet before, we can now explain a lot more about the situation of an unloaded crane on a barge and the stability as a result. At the left we can see a crane illustrated by a red line on top of a barge with a center of gravity which is finally shifted up a little bit because of the mass of the crane to the position of G, ending up with a length of the pendulum, the GM value. As we know, the stiffness of such a system is being determined by the length of the pendulum and the complete water displacement, so the complete mass of the system. In this movie, we can only change the water displacement, so the mass of the complete system, the pendulum length, so the GM value cannot be changed. However, the principle is quite clear, I think.
Show you now the situation of a unloaded crane. That means we have the mass here of the vessel. There is no load located at the top of the crane. So an unloaded crane. What happens with the stability? Firstly, we will show you the stability of this unloaded situation of the crane. Now we will simply show you what happens when we have a smaller barge or a smaller water displacement by means of having a lower mass. So we decrease the amount of mass here and we will see what happens with stability. You see that stability is already decreasing, and now a little bit more mass decrease, what happens then? And you will see that it decreases every time you decrease the amount of mass, simulating the amount of water displacement of the complete vessel or barge. And now the situation here, you will see that it is significantly decreasing in stability, and there is a moment in time that the situation is completely unstable.
In this sheet, the test setup will be used to explain what happens with a loaded crane on top of a barge. In the sketches, you see at the left side a load hanging on top of the crane. When no side leads and off leads are assumed to be present in terms of dynamics, it can be simplified by putting the center of gravity of the load on top of the crane. That is being shown in the middle of this sheet. And now we will show you the technical test in order to show you what happens.
Load, this is the load which is being picked up from the deck. When it's picked up from the deck, it's getting airborne, and at that very moment in time, the COG position is not located here anymore, however is changed to the top of the crane. However, the load is still visual here in the actual world. Stability wise, it should be taken into account at the very top of the crane. So that's a very progressive effect, because the mass will be decreasing here and increasing here, and that total effect will mean that the stability decreases significantly, which you will see. Firstly, the stability. The load is being picked up from the deck and is located at the very top of the crane, and you will see how this changes the stability of the complete system.
As you can see, it's a very simple clarification for the fact that a load is being picked up from the deck, and at that very moment the load is getting airborne only 1 centimeter. Visually there is not any change, however mathematically there is an enormous change. The center of gravity should be taken into account in the tip of the crane, and the complete stiffness of the complete system is significantly decreased during that 1 centimeter of lifting of the load. In this sheet, the test setup will be used to show you what happens when the load line is dynamically influenced. This means the load line can have an off lead or a side lead relative to the boom, induced by dynamical effects of the vessel or the pickup point of the load, or wind or other weather influences. There are all kinds of effects which can induce an off lead or side lead of the load line. The setup will show you what happens.
The real practical situation is that there is a load line in between the load and the top of the crane. That means stability wise the mast should be taken into account on the very top of the crane. However, there is also a swing possibility of the load line. So the load is being picked up from the deck and will be positioned at the very top of the crane by means of a load line. And now you will see that there is a possibility to give a little bit swing to the load line by means of an off lead or a side lead, which will induce additional moment and will also induce additional destabilization of the complete system.
As promised at the start of this presentation, we would learn to you a quick scan technique in order to determine the stability of a crane barge combination using these two pendulum principles, the load line and the GM value, which you can see at the right picture drawn in blue dotted lines. Both have a stiffness which you can calculate. At the left bottom, at the left top, you see a real life accident in which these two stiffnesses are being calculated. First, the pendulum of the GM value, the complete mass, so the complete water displacement multiplied by the gravitation multiplied by the GM value gives you a 387 kilonewton-meters per degree, and the stiffness of the load line. The load multiplied by the gravitation multiplied by the length of the load line results in a 634 kilonewton meters per degree. When you relate these two stiffnesses, you have a kind of amplification factor or sensibility factor, so you like, which give you a clear feeling about what happens. What does that mean, a amplification factor of 1.64? That means that an off-lead angle of 1 degree will result in a heel of the barge of 1.64 degree. This is a very fragile situation, quite clearly. But what value is safe and what value is not safe? It's a little bit arbitrary. However, for at Eagle 1 we use at this moment a 0.5 as a maximum for a safe situation, and at least this value should be below 1, as you can understand. However, with certain safeties, 0.5 is a good value to start with. In order to have a exact detailed stability calculations, you always need more than just this quick scan. However, for just interpreting a first rough guess, this is a very, very good principle to use. Now we know that we can do a quick scan on stability of a crane on a barge. It is good to know, as a side note to this presentation, that always ratings are needed to have a safe situation. Ratings are always needed when you have a combination of a crane on a floating support. And it's good to know that when you have these ratings, you're always safe. because in these calculations of these ratings, the situation of the barge, the metacentric height, the stiffness, the elasticity of the complete system where you're standing on is embedded in the calculation. So when it doesn't tip in the calculation, then the ratings are a determining factor for a safe lift. So the quick scan is still very useful in case you still not have these ratings and you want to have a quick feeling about whether it's possible to put that crane on that barge and to do the lift with the equipment you have. And after that, you can ask yourself the question, let's make some ratings for this combination, and after that do the job. So that about ratings as a side note to this presentation. Now we have come to the end of this presentation. In this presentation, we have learned you a quick scan technique in order to determine the stability of a crane on a barge. A quite useful technique to have a clear view about the stability when time is limited. Side note to this presentation was the simple fact that for safe liftings you need ratings. Always you need ratings. So this quick scan technique is a tool to have a quick scan for possibilities in terms of cranes, barge combinations which are available and possibly can do the job. I hope you have learned from this presentation, enjoyed it, and hopefully we meet in a next presentation. Thank you very much.